Yeah, and from now on, we are recording as well. And Ian, can you see your advertisement screen slide?
Yes. Yeah.
Okay, good. In the past, there was sometimes an issue that it wouldn't show.
It would be awkward.
So good morning, good afternoon, good evening, everybody, and welcome to this week's EMinar. I see people are still pouring in, but while you're doing this, I just want to alert you to the EMinars of the upcoming weeks. So as you all know, today we have Ian Ferguson on nuts and bolts of magnetotelluric instrumentation and fieldwork. So I think that's going to be very interesting on a sort of practical level, how to acquire MT data. And I'm sure the vast majority of you know Ian. Next week, my screen doesn't want to change. Next week, we're going to move to sort of, if you want, so a bit the opposite side, modeling and inversion. So Raphael Rochlitz will talk about CAST-EM from open source 3D EM modeling towards inversion, so numerics and computational issues. Then on the 23rd of March, we have something that goes a bit beyond just electromagnetics. Simon Jowett on mining for, I think that's supposed to be net zero instead of new zero, so mining for net zero. Of course, EM has a big role to play in that in terms of exploring for new mineral deposits. And then on the 30th of March, there's Seogi Kang on advancing Earth imaging techniques for improved understanding of groundwater systems. I assume all of you know this page by now quite well, but if you want to know what's going on beyond the 30th of March, look at previous videos and look at the presentations. You can find that on the MTNet EMinars page. There you can also register for the upcoming EMinars. And we are in a webinar after 2 years of COVID. I think everybody has experienced these at least once. The main thing is that please, if you have questions, put them in the Q&A and not in the chat. So far, we've always done it that we've handled questions at the end, and I think that has worked very well. If there's a really urgent questions that needs to be answering while Ian is speaking, I will monitor everything, and I can you can put a little note there, and I can stop Ian and ask that question. But yeah, typically the discussion at the end has worked very nicely so far. And with that, I'll hand over to Ian to share his screen and talk to us about MT, nuts and bolts of MT.
Okay, I think we're ready to go. Thanks very much, Max. It's a pleasure to be here today to talk to you about MT instrumentation and fieldwork. As indicated by the nuts and bolts in my title, the presentation is intended to be one of the EMinars that's of a tutorial nature, with the focus of the talk being suitable for those who have less experience in MT fieldwork, but who would like to know more. I start by admitting that I'm not an MT instrument engineer or an instrument physicist or a field acquisition specialist, and I feel that I'm really presenting today's EMinar on behalf of those members of our community. We haven't had too many talks in the series focused on MT instrumentation, and I hope this presentation will prompt some others. There are many people out there with deep insight and experience in designing and building and using MT equipment that we would all benefit from hearing. I am fortunate to have had a reasonable amount of field experience doing MT, and have been involved with either MT, telluric, or magnetic measurements in 2 different hemispheres, from the sub-Antarctic to the subarctic, on land and in the marine environment, and perhaps, unfortunately for me, most notably over 5 different decades. So how did I end up here today giving a talk on instrumentation? Partly by chance, I ended up writing the chapter on instrumentation and fieldwork in the MT book by Alan Chave and Alan Jones. Alan then asked if I'd present an updated version of the chapter in the EMinar series. So after sort of mildly resisting for about a year, here I am today. And I refer you to the book for any additional details that I won't be covering today. But I'd also like to note that there are many, many other monographs and papers out there with information on MT instrumentation, just a very small number of which I've pictured here. If you are more experienced in MT, I hope you'll still learn something useful today. And if not, there's a chance you might see your work used in the presentation. And finally, I should say that in today's presentation, I'll use examples and pictures from many different instrument companies. There's no intended endorsement of those companies, nor intended rebuff of the companies whose pictures I'm not showing. I've really just used a subset of the information I have on hand and that came up very early in Google searches. So I'm going to start with a picture of an MT system from Kivevozov in 1972. Notably, this picture is now 50 years old as of this year. He shows MT systems consisting of magnetic channels, electric channels, and acquisition devices. And this picture is still very much accurate today. In my talk, I'm going to have a few slides on the requirements of MT measurements. We will then look at electric field sensors, magnetic field sensors, and more briefly, MT recording devices. And the focus of my talk today is going to be really on traditional land, natural source MT measurements. There are 2 other EMinars that have been given in the series that are directly related to today's talk. And of course, other EMinars also had some relationship to it. In the series last year, Alan Jones presented on MT acquisition from survey design to field procedures. And just a few weeks ago, Adam Schultz presented on faster, lighter, cheaper, developing new instrumentation to broaden access to MT. I'm going to try not to overlap too much with those 2 presentations, and I encourage you to take a look at them if you weren't attending them on the YouTube. I mentioned that Kiva's image was more or less still relevant. There are a couple of points that are out of date. In his system, he shows the analog to digital conversion being based on only 10 bits. The data storage was based on a digital tape recorder. And although not shown here, the system certainly didn't use GPS timing. And I think these are 3 of the biggest areas in which the most changes occurred in MT acquisition over the last few decades. Adam, in his presentation, talked about 32-bit acquisition and telemetry and the importance of those in modern MT surveys. So we start with the requirements of MT measurements. And I think most of you will know this, but it's useful to articulate what we're trying to do with the MT instrumentation. And that, of course, is to record time series of the 2 or 3 components of the magnetic field or magnetic induction, and 2 components of the horizontal electric field. And in addition, 2 remote components, Rx and Ry. And we want to make these recordings with high signal to noise ratio and for signals over a broad period range encompassing the resolution of depth that we're interested in. The recordings must allow computation of unbiased, low variance, 4-component impedance responses, and possibly the tipper response over the target period range. In order to achieve this, the signal at the remote reference site must be coherent with the signal at the main site. It doesn't have to be identical, it just has to be able to be related to it through a frequency domain transfer function. The noise must not be coherent between the remote and the main site. The remote reference, of course, is usually a pair of horizontal magnetic field recordings, but electric field recordings are sometimes just as effective. And finally, our computed MT responses, to the greatest extent possible, should correspond to 0 wave number geomagnetic sources. So in summary, we want to record something like this, a series of nice time series from Matthew Como from the Central Andes. And we want to use those to compute high quality, low variance impedances, such as these from a broadband MT response from a remote area in southwestern Australia. In order to understand the necessary specifications of the equipment we'll be using, we need to look at the signal levels that we'll be measuring. And this slide just compares 2 typical signal levels. In this case, it's from 2 Proterozoic sites, a relatively resistive site from the Grenville origin in Canada, and a relatively conductive site from the Fraser origin in Australia. We see that the magnetic levels are fairly similar at both of these sites, and for the north and east components of the magnetic field. But I should mention that for short periods of time, several days, the signal levels might be a factor of 10 or even 100 times smaller than these levels shown here. In the case of the electric fields, we see a very big difference between the fields at the resistive site, which are larger, and at the conductive site. There are many papers out there describing the background sources of signals. Some of the things that are notable, of course, are the presence of the AMT deadband and the MT deadband, and other locations where we have enhanced signal levels, such as associated with the Schumann resonances, and here with the PC1 pulsations. And as mentioned, in the case of the electric fields, we may have fields that are a factor of 100 or more larger at a resistive site than at a conductive site. So our equipment should be capable of measuring the electric fields at the most conductive sites that we have in our survey area. And sometimes, of course, we're in the less favorable situation of a site with a very anisotropic MT response, when one component might be at this level here, and one component might be at the very different level of signal. We can, of course, divide the MT acquisition into, if you like, the traditional bands: audio frequency magnetotellurics, broadband magnetotellurics, and long period magnetotellurics. There's still some validity, I think, in these classifications. For instance, the signal level for AMT is typically involving atmospheric sources, whereas for LMT, long period MT, it's going to be dominantly magnetospheric sources. LMT surveys will typically use flux gate magnetic sensors, whereas BBMT and AMT surveys will traditionally use induction coil magnetic sensors. But from an instrumentation point of view, I think these classifications are becoming quite blurred now, and there is a lot more overlap between the different types of surveys. Okay, so we'll now turn to electric field sensors. On initial consideration, it appears we have quite a very simple task of measuring electric fields. All we've got to do is lay out a couple of wires, connect them to the earth at either end, and make a measurement of the potential difference. However, when it comes to the detail and making accurate measurements, there's a lot more that we have to worry about. The MT electrometer, of course, measures the electric field in 2 horizontal orthogonal directions. And on land MT surveys, this is usually done by measuring the potential difference between grounded electrodes spaced by a known distance. And in most cases, this distance is between about 25 meters in AMT surveys up to several hundred meters in longer period surveys. And that's illustrated in this diagram here. Most MT systems also use a ground electrode near the recording unit, and this also serves as a grounding electrode for the electronics in the acquisition. Most land MT surveys, of course, use non-polarizing porous pot electrodes, so copper sulfate, lead chloride, cadmium chloride, or silver chloride electrodes. Some high frequency surveys use metal rod or metal plate electrodes, such as shown here. And some high frequency radio magnetotelluric or audio magnetotelluric studies might use capacitive electrodes as well. So let's just take a quick look at the physical principles. The electric field that we use in MT can be described in different ways. One way is in terms of a scalar potential and a magnetic vector potential. The presence of the second term in this equation here means that the electric field is non-conservative, and therefore the potential difference between 2 points depends on the path of integration or the path of the wire between those 2 points. So for measurement of potential difference to provide a measure of the electric field in a direction, it's necessary for an unshielded wire joining the electrodes to be straight. What are the errors associated with this requirement? As indicated here, the errors could rise to a few percent in apparent resistivity or a few degrees in phase if the average deviation from a straight line is a small fraction of the skin depth. So as a result, these errors are going to be highest at the higher frequencies. Of course, in the extreme case, if we have excess wire and we use it to form a large circular loop on the ground, the time variations of the vertical magnetic field will induce a spurious voltage in the loop that's proportional to the area of it. So if we ever have excess wire, we should fold it back along the line of the actual sort of line of the measurement that's being taken. Okay, so again, as mentioned, it should be an easy operation to put an electrode in the ground just to make contact, but it turns out that it's actually quite a complex measurement to make. We would like to measure the telluric potential in the ground, but in fact, the measurement we make is going to depend on many factors that include the soil in which the electrode is located, the electrode itself, the electrical characteristics of the wire joining the electrode to the recording device, and the recording device itself. Overall, it's desirable for the half cell potential, E1/2 here, of the electrode to be as low as possible. The series resistance, capacitance, and inductance of the system to be as low as possible, and the parallel impedance in the recording device to be as high as possible. So now we're going to take a look at a couple of these factors, starting with the half cell potential. So variations in half cell potential will depend on the ambient conditions, moisture content, temperature, and so on. And there'll also be some variations that are independent of the ambient conditions, including the deposition of metal iron salt on the metal interface and physical degradation of metal surfaces in the electrodes. For metal type electrodes, such as the rods or plates I mentioned earlier, there may be spontaneous changes in the potential, and these might be as large as 20 millivolts. and this is due to reaction charge release. The time frequency characteristics of the noise will be different for different types of electrode. And the electrochemical processes involved are complicated and depend on the frequency, current density, and also on the ambient conditions. I like to look at the results in terms of this study, in which different electrodes were used to measure the voltage response in, I think, of 60 ohm meter tap water. So in each of these cases, a sinusoidal signal should be seen in the responses. And here we're looking at 10 kilohertz signals, 1 kilohertz, and so on. We can see that as we move to the lower frequencies, we start to see some more erratic responses, such as here. And as we go to a 10-second signal, we start to see very erratic type results. And these are particularly occurring in the aluminum and in the steel electrode, whereas the acid-free steel, platinum, and reference electrodes are more stable. So we see that the electrode noise of metal electrodes increases as we go to increasing period. In general, for metal electrodes, stainless steel provides the lowest noise levels, followed by iron, copper, lead, brass at intermediate levels, and aluminum and graphite are not particularly good at all. And in general, the level of spontaneous noise, features such as the one we're seeing here, will increase with the increasing self-potential of the electrodes. So if we turn from metal electrodes to metal ion electrodes, in that case, the half cell potential is mainly due to the potential between the metal and the surrounding salt solution. However, there is also a contact potential that occurs when the electrode is put into the soil. And this normally dissipates within a few hours of the installation. Here's an example from Simon Andrus's webpage, showing an example of the decay of the contact potential between the electrode and the ground, and we see it dissipates over about 100-minute time scale. So in this case, the contact potential is caused by the liquid junction and diffusion potentials that are also observed in SP logging in the petroleum industry. And it develops because of the different salt concentrations in the electrode and the soil, and the different mobility of the different ions involved, the sodium, the chloride, and so on. Okay, so if we put all this together, the half cell potential will represent electrode noise. So for the MT book, I completed a synthesis of a variety of different noise results from different studies, and that is shown here. So this is showing the noise of the electrodes expressed in terms of voltage squared per hertz as a function of the period. The noise levels can be compared with the background signal levels for a resistive land site and a conductive land site. And overall, we see that the impact of the electrodes is likely greatest in this period range here of around sort of 1 to 10 seconds. For recordings in this range, this is where it's most important to have our electrodes being good quality electrodes. Overall, we see that the electrode noise increases with increasing period. We always have a positive slope on this log-log graph. And this applies to both metal salt electrodes and for metal electrodes. The relative difference between metal electrodes, these guys shown up here, and the metal ion electrodes shown down here, that difference decreases as we go to higher frequency or shorter periods. At 1 second, we have about a factor of 10 difference. And by the time we get to 0.1 seconds and higher frequencies, the metal electrodes are providing comparable performance. And that's why we can get away with using metal electrodes in, say, AMT surveys with similar responses. Good quality electrodes have the responses shown by the asterisks in this diagram. We'd like to have noise levels, say, of around 10 to the minus 14 volts squared per hertz at 1 second period. And this will correspond to a mean peak-to-peak fluctuation of about 0.3 microvolts at that period. And the results for the longer periods are also shown on this diagram. Exceptional electrodes might have a noise that's in terms of the power, that's a factor of 50 or more better, shown by the green arrow. And poor electrodes might have a performance that's a factor of 10 or so worse. For electrodes of any particular design, it's been found that the noise is associated with the half cell potential has an approximately Gaussian form. So therefore, by using pairs of electrode with similar self-potential, you can minimize the differential potential during recordings. And a final note is that in general, the electrode noise is worse in land deployments than in the lab because of the more variable conditions. Okay, a few words on electrode drift. And this figure is just showing a typical metal-metal ion electrode. As mentioned, soil chemistry and moisture changes can cause long-term change in electrode potential. Following installation, there's a stronger drift over minutes to tens of minutes associated with the dissipation of the contact potential. Temperature is important, and of course, the worst temperature effects will be seen in the longer surveys that expose electrodes to the largest temperature variation. Freezing is an issue. As freezing occurs, the salinity of the unfrozen pore fluid will increase, changing the chemistry, changing the electrode potential. And then finally, at even colder temperatures, as the ground and possibly the electrode itself freezes, quite large increases in potential and resistance will be observed. And so other methodologies have to be used for metal deployments on ice or in completely frozen soils. And I'll mention those again in a minute. Undesirable electrode drift also occurs because of the aging and deterioration of electrodes, and these might include changes to concentration of metal ions, corrosion of wire in the electrode, or the presence of any exposed wire outside the electrode. Okay, we'll turn to electrode impedance, or the in-phase component of impedance, the resistance. The resistance of an electrode, the stuff happening inside this box here, is often measured in terms of an equivalent Randall circuit. What's in this circuit? It'll include a Faradaic charge transfer resistance, the normal resistance we think of in terms of the contact resistance of an electrode. We also may have a Warburg impedance that's associated with the transfer of ions to the electrode surface by diffusion. And there might also be a capacitance associated with the charging and discharging of this, the ions that are sort of in the organized part of the aqueous fluid adjacent to the electrode and to grain surfaces. So the processes are quite complex. Overall, the electrode impedance or resistance will be frequency dependent, and to an extent, it'll also be current and voltage dependent. Accurate measurement of the potentials also requires the electrode contact resistance to be reasonably small. Large contact resistance will couple with the capacitance of the dipole wires to affect the shorter period responses. And Zong and Hughes showed that as a rule of thumb, this effect becomes significant if the product of the wire length, the frequency, and the resistance in kilometers, kilohertz, and kiloohms exceeds 2. And I put this information together just in a quick illustration here. And it's showing the log of the contact resistance versus the log of the frequency for different electrode line lengths. And the colors of red to brown here are the less desirable responses, where this factor is above 2. And we can see here that for a not crazy contact resistance of around 20 kiloohms, we're going to start to affect the MT response at periods above about 1,000 hertz. And this is for a 25-meter line. For a 200-meter E line, the effects of a 20 kiloohm contact resistance will start to kick in at just a few hundred hertz. And this shows an example from Alan Jones from a survey on frozen ground at Baffin Island. And here we can see that at periods shorter than about 0.1 seconds, the phases are going to 0 or 180 degrees. And there's a strong fall off, approximately 1/f fall off in the apparent resistivity responses. And this is indicative of this effect caused by the contact resistance and the capacitance of the wires. So what is that contact resistance? It's going to depend on the shape and size of the electrode and the resistivity of the surrounding material. There's a formula here and a result for a rod-shaped electrode. And it turns out that for, say, a 1 centimeter diameter rod buried to 50 centimeters in a half space of 1,000 ohm meters, the contact resistance will also be about 1,000 ohms. So for most rod-shaped electrodes, the contact resistance will be numerically similar to the value of the resistivity in the near surface material. If we turn to metal-metal ion electrodes, there'll be an internal resistance between the metal and the salt inside the electrode. And this is ideally less than several hundred ohms, although it can become a kiloohm in poor or old electrodes. And there's also a contact resistance between the base of the electrode and the ground. The contact resistance with the ground is often the smaller term, but in dry, sandy soils, it can become the larger component. And of course, the overall contact resistance can be reduced by using twin electrodes connected to the ground in parallel. If none of this is adequate to reduce the contact resistance, it may be necessary to use active electrodes, as have been used in Antarctic surveys. And this shows the schematic of the circuit design for the active electrode used in Antarctic surveys by Phil Wanamaker and his group. There's a preamplifier that amplifies the electrode response near the electrode, and then the signal is taken by shielded wires to the acquisition device. This is a more recent picture from Kerry Key's group showing the titanium plate electrode and preamplifier, which increases the signals and removes this filtering effect due to the contact resistance. Okay, so that's the electrodes themselves. There's a lot to talk about. If we look at some of the other components of the electrode system, telluric amplifiers, differential amplifiers, they will typically amplify the signal either between the east-west and north-south electrodes, although some systems amplify the signal between the individual components, say western ground, eastern ground, and so on. In the second case, instruments of the second design, it's really important to use a good quality ground electrode that matches the quality of all the other electrodes. Otherwise, if there are spikes or drift or other bad effects associated with the ground electrode, they may cause saturation or other effects on the amplification of the signal. Amplifiers should be matched to the electrode impedance. They should have a linear response over the range of input values, input voltages and periods. They should have low noise relative to the electrode noise. And of course, they should have low temperature dependence and moderate power consumption. Noise can be minimized by using chopping amplifiers, in which the output is reversed in sign at short period duration segments and integrated. The chopping amplifier will reduce drift and remove DC offset between channels and allow measurement of a long period response, but it will affect the frequency bandwidth of the output. Finally, electrometer field deployments. Of course, the deployments are usually in a cross shape or an L-type shape, often in geomagnetic or geographic coordinates, and with accurate GPS measurements, the geographic coordinate choice is becoming more common. In land surveys, electrodes are optimally deployed in moist, salted, kaolinitic mud or bentonite, and the saline fluid helps reduce the overall contact resistance, and the clays help retain the moisture. In soils with intermediate moisture level, the long-term drift can be reduced by deploying the electrodes in non-metallic buckets, the so-called Russian bucket configuration, shown here. So the electrodes in something like a plastic bucket, which is then placed in the ground. However, in very dry soils, it might be best to install the electrodes directly in the soil to allow the hygroscopic properties of the clay to attract moisture from the surrounding soil. And in very wet soils, no bucket is required, and it's sometimes recommended to use no salt. If you do use salt, the changes in moisture content after rainfall can result in changes of the soil chemistry and therefore changes in electrode potential. Okay, so that's it for electric recordings. We'll now move to magnetic sensors. And of course, the role is to measure 2 or 3 components of the magnetic induction B in 2 or 3 orthogonal directions. In modern MT systems, the measurements are usually made with an induction coil sensor for AMT or BBMT and flux gate sensors for LMT. It's important to note, though, that a large volume of long period data has been collected in the past using torsion fiber magnetometers based on observing or nulling the deflection of suspended magnets. And this is the classic Goff-Reitzel instrument that was used in many surveys in the earlier few decades of MT studies. Modern surveys might also employ Squid magnetometers. The noise level of squids is typically very good compared with that of flux gates, particularly over the sort of intermediate period range. The squids are less portable, particularly low temperature squids that required liquid helium. High temperature squids require only liquid nitrogen, but have slightly higher noise levels. So for requirements, surveys requiring really accurate magnetic field recordings, there's perhaps a role for squids in the future. But I'm just going to focus on the induction coils and the flux gates. Okay, induction coils. The principle's, of course, simple. The voltage or EMF induced in a coil is proportional to the effective area times the rate of change of the magnetic field parallel to the coil axis. However, the practical response is also going to depend on the lumped resistance, capacitance, and inductance of the coil. And as long as the input resistance of the coil is much less than the measuring device, the corner frequency will be given by this formula here. There will be a drop-off in the high frequency response after frequencies above this value. And for this rollover frequency to be high, it is desirable for the capacitance, and that depends on the coil geometry, the wire diameter, insulation characteristics, and sequence of winding, to be as low as possible. In order to minimize noise levels, it is also desirable for the resistance, which depends on the gauge of the wire and the metal used, to be as low as possible. The sensitivity of course, can be increased by the addition of magnetically permeable material within the core of the coil. And here we have a picture showing the windings going above and below the coil, and the magnetically permeable material shown here. And so various materials can greatly amplify the response. However, geometrically controlled demagnetization means that the net permeability of the coil is going to be less than the permeability of the material used. And that's shown on this figure here. For instance, what it's showing is the net permeability versus the ratio of the length to the diameter of the coil. So for instance, if we have a material with permeability of 10 to the 4, relative permeability of 10 to the 4, the coil itself will only have this permeability if we have an extremely long, in this case, over a factor of 1,000, length to diameter ratio. Overall, the demagnetization, however, is minimized when the core has a long rod-like form. The induction coil response also depends on the characteristics of the measuring electronics. And if the ratio of the coil resistance to the load resistance is significant, the response will have a flat peak with the corner frequency specified here. Preamplifiers are now constructed as part of the coils and must be well matched to the coils to provide a relatively flat response in the target period band. So there are many factors that have to be balanced during coil design to produce the desired system response, the required noise levels, and functional aspects such as the coil dimensions and the mass. And this slide just shows an example in which nonlinear optimization was applied to coil design. It's showing the number of windings versus the wire diameter. And the black curves show the noise level of the system. And the desired noise level here was 1 picotesla at 1 hertz, and that corresponded to this point here. The color lines show the mass of the coils in kilograms. So in this case, the desired noise level was obtained at a 0.4 kilogram coil. And this example comes more from a control source, EM, rather than MT. But there's also been considerable effort in MT over recent years to produce coils with broad frequency ranges to permit both AMT and BBMT recordings, and sometimes LMT, using a single sensor. And manufacturers now can provide coils with a period range with some reasonable response between about 10 to the -4 and 10 to the 4 seconds. However, there are still some advantages in using multiple sensors with narrow bandwidth in certain situations. And these include a greater sensitivity and flatter response in the desired period band, minimization of noise associated with signals from outside this band. In some cases, for instance, if we're looking at an AMT survey, we can use smaller coils if we're just using a narrow AMT after a narrow AMT response. And sometimes individual sensors may provide lower power consumption. We will typically look at the properties of coils in terms of the sensitivity, the amplitude and phase response, and in terms of the noise spectrum. So this very busy slide shows a synthesis of responses from many coils, most of which are used in MT surveys. And we're going to look at some of these individually in the next few slides. For comparison, the black lines show induction coil responses, and the red lines show flux gate responses that are flat with zero phase within, as long as we're above the period range of the measurement cycle. So we see that there is some variation in the sensitivity, the number of volts we generate for a nanotesla signal, and also in the phase response. Typically, the amplitude response is fairly flat over the period range of interest, target period range. And the phase will pass from very low values through 0 to higher values in, again, this period range of interest. The inclusion of integrating circuitry reduces the fall off in the long period response, so moves us in this direction, and also drops the long period phase response from 180 down to 90 degrees. So here I've just highlighted those coils that have an AMT focus. And of course, they tend to be flatter for the flatter responses for the period range from about 10 to the -4 through to around 1 second. And the phase passes through 0 in that same period band. These are some coils with an empty focus. And we see great diversity here, but in general, the peak response is occurring around about 10 to the 0 or 1 second period. Some of the empty coils provide excellent responses moving into the AMT range. Other of the empty coils provide more of a LMT response as we move out to longer periods. Finally, there has been development of coils that have a very broad period range, and some of those are just shown here, which will allow some combination of AMT, broadband MT, and long period MT type responses to be obtained with the single coil. And this is, again, one of the changes that has occurred since the production of the MT book, the availability of these broader band coils. If we turn to coil noise, again, we want the noise characteristics of the coils to be well below the MT signal levels. And of course, the MT deadband is going to be one of the areas in which this requirement is the most challenging. The noise in the induction coils arises from the coil itself and from the electronics, including the amplifier. For the coil itself at higher frequencies, the source of noise is the thermal resistance noise or the Johnson noise of the coil wiring. This will increase with the resistance of the wire. At high frequencies, current noise in the amplifier becomes the most significant source. At very low frequencies, the noise in the spectrum is dominated by 1/F noise from semiconductors in the circuitry. Overall, a good induction coil sensor has a noise level of less than about 10 to the -8 nanotesla squared per hertz at around 1 second. And this will correspond to mean peak-to-peak fluctuations of less than a picotesla. Note that the response of a coil may change with time due to aging of the cores, the different response of the cores in the different Earth's field strengths, changes to the core material due to ambient conditions, and changes in the coil geometry, such as due to bending or distortion. Bottom line is coils should be calibrated regularly. We should also keep in mind the air loop sensor for vertical measurements. This will typically have a similar response to other induction coils, although it may have slightly less sensitivity than some corresponding coils for this, coils in this providing responses in the same bandwidth. Okay, so flux gate sensors. Flux gate sensors will consist of an excitation coil wound around a magnetically permeable body, here a ring core flux gate sensor, with a detector coil. The differential magnetic saturation in directions parallel and anti-parallel to the Earth's field provides a measurement of the field magnitude. As mentioned, the sensitivity of flux gates is flat and has zero phase at periods significantly longer than the measurement cycle. And the amplitude response is typically in the range 0.5 to 10 millivolts per nanotesla. This value is restricted more by the amplifier and the recording electronics than the sensor itself. And generally, I won't show the figure. At periods longer than about 1,000 seconds, the flux gate sensors will have superior sensitivity to the induction coil sensors. Flux gate sensor noise. The noise will come from sensor noise, thermal drift, and long-term drift. The sensor noise arises because basically materials are not, they don't have ideal magnetic characteristics. When they're magnetized or demagnetized, the magnetization state changes in a series of small discrete steps called Barkhausen steps. And these are caused by the influence of the crystal structure or the material structure on the response. So we don't measure a purely ideal hysteresis loop. We have these small jumps and irregularities that occur. This noise can be minimized by appropriate choice of core material, and researchers have shown that metallic glasses consisting of alloys of iron, cobalt, silica, and boron have suitable properties. The cores generally show a 1/F noise characteristic, and typical noise levels of between 2 and 8 nanotesla squared per hertz at 1 hertz frequency. The thermal sensitivity or thermal noise arises mainly from the circuitry. Studies have shown this might be around between 10 and 0.5 nanoteslas per degree, whereas the sensor itself has typical sensitivity better than about 0.1 nanoteslas per degree. So the electronic matters in terms of the noise. And again, there is a long-term drift that studies have suggested that drift values of 1 nanotesla per year, which should be more than ideal for MT, might be possible. Overall, flux gates provide excellent noise levels at a particular level of power consumption, for example, compared with induction coils. For the flux gates themselves, there's an overall correlation between decreasing noise level and increasing power consumption. So this is a trade-off between obtaining the noise levels of a particularly low level and increased power consumption. Okay, other components of magnetometers. Of course, one is the Powerline filters, intended to filter 50 or 60 hertz powerline signals and their harmonics from the data. And these signals occur within the BBMT frequency range. Powerline noise is usually removed using comb filters, acting on the primary frequency and its harmonics. For symmetric clipping of the response, 60 hertz response, only odd harmonics will occur. But ideally, the comb filter should also filter for even harmonics so that the instrument can be used in areas with an unbalanced power supply. And this just shows an example from a recording that we made near the Boundary Dam Power Station in Saskatchewan. It's a recording using Phoenix equipment of 3 different sampling rates, 150 hertz, 2400 hertz, and 24,000 hertz sampling. The signals include 60 hertz signals and some pipeline maintenance signals, this broadband response shown here. In the lower 2 sampling frequency results, comb filters have very effectively removed the 60 hertz and its harmonics. However, no filter was applied in the higher frequency sampling, and we can see the presence of harmonics from the fundamental through to at least the 19th harmonic at almost 1200 Hertz. We possibly would have seen more with a log scale. So something to be aware of, that the 60 Hertz signals and its harmonics can extend to very high frequencies. Low-pass filters are needed to remove high-frequency noise, such as VLF radio frequencies, and it's sometimes tricky to get the roll-off of these filters correct to enable the removal of, say, VLF signals, but at the same time preserve the AMT frequency range. Magnetometer deployment. Generally, the magnetic sensors are buried to between 20 centimeters and 1 meter to minimize temperature variation, microseismic shaking, and wind noise. Sensors should be installed using compasses and levels to an accuracy of 1 degree. Here we have installation of induction coil, and here of a flux gate sensor. For longer period surveys, it's critical for sensors to be installed in firm soil to minimize long-term drift due to sensor orientation changes. A change of only 0.1 degree in the orientation of the instrument can produce a change of 100 nanoteslas in the 60 nanotesla earth field. Finally, installing vertical coils can be a challenge, but for those who are a little older in the audience and have installed Goff-Reitzel instruments, you'll know that it doesn't really even compare. Okay, finally, a few words on MT recording devices, just to finish off. The number of bits, we'll start with digitization and dynamic range. And the number of bits used in this process, the digital to analog conversion, analog to digital conversion, affects the dynamic range. And the dynamic range, of course, is the ratio of the largest to the smallest measurement that is possible, expressed in terms of a log scale. Modern MT instruments tend to have 24-bit, or as Adam talked about, 32-bit resolution, providing a dynamic range in terms of signal power of over 130 decibels. This compares with older systems with a dynamic range of only 90 decibels or less. For LMT, this is important. The 24-bit system allows us to both record the total Earth's field and smallest measurements of around 6 picotesla. This value corresponds to a noise level at 1 second that is just below the inherent noise of a good flux gate sensor. So the 24-bit system allows us to record essentially from below the noise level of the sensor right up to the value of the Earth's field. And this is important. It means we don't have to subtract off a baseline value and record it separately from the Earth's field. For induction coils, the Earth's field is not a constraint, of course, because we're measuring the time derivative of the field. And the time derivative also flattens the spectrum. So 24-bit systems allow accurate recording of the signal during both quiet and disturbed periods, but also allows accurate recording of narrow band noise that's superimposed on this background. For electric fields, the 24-bit system allows a maximum of 1700 millivolts, large enough to accommodate most electrode drift, and at the same time allows the smallest values of around 0.1 microvolts to be recorded, and that's again sort of matches the signal levels that are desirable. In his talk, Adam mentioned some of the advantages of 32-bit systems. It's certainly, they're going to allow much more accurate recording of the various noise sources, and also accurate recording of the natural sources during very quiet times. data acquisition and storage. And I'm going to illustrate the next few slides just with a few different samples of different MT systems. Data acquisition is controlled by an onboard computer. Typically for each run, a program to be executed or table of parameters is downloaded from a PC, memory card, or other storage device or programmed interactively. One of the most important advances in MT instrumentation in the last few decades has been GPS synchronized data acquisition, which provides an accuracy of several hundred nanoseconds. Data are now recorded with solid state memory, such as memory cards and solid state hard drives. Telemetry is of growing importance, and again, Adam discussed that in his EMinar. Typically, data volumes are now several hundred megabytes or more of MT data at each site for broadband and AMT surveys, and up to around 1 megabyte per site in long period MT surveys. Most LMT instruments record continuous time series with a fixed sampling interval, and there is little to be gained by using shorter sampling periods. AMT and BBMT systems typically use more advanced recording arrangements with 2 or more frequency ranges. The recordings in these frequency ranges will use a different base frequency sampling rate and recording window lengths, and sometimes different amplifier and A to D boards. One issue is the AMT deadband, and the signal levels in that band are typically 1 or 2 orders of magnitude lower than the sensitivity of most sensors. Strategies for optimizing the data collection in this band include nighttime collection when signals are stronger and threshold triggering of buffered recordings. In CSAMT and RMT, the MT response is usually measured at a series of discrete frequencies or periods. The MT response may be computed on board with no need to record the time series. Power requirements and batteries. Most land, BBMT and AMT systems have power consumptions between 5 and 15 watts and will draw around 1 amp with a 12-volt supply. Typically, they can be operated for 1 to 2 days using 1 or 2 good quality wet cell car-type batteries. For LMT systems, the power consumption is significantly less, typically 1 to 2 watts. And these systems are usually going to require 1 probably higher quality wet cell battery per week of recording. Solar panels are, of course, becoming more commonly used in long duration and remote recording locations. They do have some associated issues, such as noise generation and security. My own experience has been that they seem to form good target practice for locals practicing their shooting. Finally, 2 slides on calibration. MT equipment must be accurately calibrated. And for broadband MT and AMT, it's necessary to conduct a frequency-dependent calibration. LMT can often be done using just a single period, such as DC. The first step in calibration is ensuring that the recording unit responds correctly to the input signals. And this can involve using a reference voltage input to simulate a sensor output to ensure that it's recorded at the correct level. The second part involves defining the separate response of each sensor, including its preamplifiers and filters. And coil sensors are usually calibrated using a secondary coil generating an accurately known field. For BBMT and AMT with significant period dependence, the calibrations are usually applied to the frequency domain response during data processing. And finally, it's important for the MT systems to be tested for instrumental and other noise levels prior to their use. And this can be done at different levels. Firstly, it's possible to make recordings in an area in which noise sources are at a relatively low level, and then examine the spectra of the recorded time series for indications of noise. So this might include spectra that have flat regions indicating a random response, or spectra that have 1/f responses indicating an instrumental noise. This is an example from northern Manitoba in a remote area where we recorded on 2 consecutive days. On the first day, the signal level was exceedingly low, and we see we have a flat response at higher frequencies here, indicating that we've reached the, if you like, the resolution level of the system. We could also identify a source of narrowband noise here that turned out to be associated with a hydroelectric facility about 200 kilometers away. In contrast, the next day, the signal levels were higher, so we see a more accurate MT spectrum. The second component of the noise testing is side-by-side tests. So for coils, side-by-side tests will provide an indication of the frequency-dependent noise levels. Electrodes can be examined the same way and possibly should be, but we often will look at electrodes using a DC approach, for example, with the voltage measured between different pairs of electrodes placed side-by-side on cloth or paper moistened with a saline fluid. And finally, the full MT response of a system can be assessed by comparing a full impedance response measured by 2 instruments at the same location. While this won't help isolate the sources of noise, it provides an indication of the overall complete response of the system, and it matches more closely what is eventually going to be done in defining the final impedances. So that's it for most of the information. I'm just going to finish with some assorted recommendations. Firstly, talk to the MT instrument engineers, the MT field practitioners. To get good results, MT equipment often needs to be more than a black box to the user. So make sure you have some understanding of what the equipment is actually doing. A second aspect, don't ignore the electrodes. I think in the early part of my career, I regarded electrodes as part of the disposable equipment in the same way as wires and batteries perhaps are. They're not. They're really part of the critical electrical sensing system. And if you're paying thousands or tens of thousands of dollars for your coils, why skimp on electrodes? Thirdly, electric field recordings can sometimes make good remote references. Don't ignore this possibility. And again, this provides more impetus to use good electrodes. Finally, fourthly, I haven't talked about it much in this talk, but good site selection is important. Good site installation is critical. It's rarely possible to use MT processing methods to get good responses from a poor site. Likewise, take really detailed, copious field notes. It's often hard to extract the information from your own brains when you get back from the field. Make sure everything's written down. And finally, wherever possible, to fully understand the MT data, look at the MT results, look at the data. If you can, have a quick look at sample time series from a survey. If you have spectral EDI files, look at spectra, signal to noise ratios, and so on to try and get an understanding for the signal and the noise levels in the survey area. So I think that's it for the technical information. I don't have acknowledgements. There are actually too many people to acknowledge. There are those who I've talked to about instruments and how they work, and what you should do in the field. But there's also really practical information you can get out there. Things like how to dig a neat hole in the field to put a sensor in, how to splice wires in the field, how to coil back up your E-lines without getting kinks in them. These are all really important aspects of field work, and there's lots of people out there who will be more than willing to show you how to do those things. So with that, I'll end. Thank you.
Thanks, Ian. That was very interesting. And yeah, a lot of aspects of MT field installations covered there. And we already have 3 questions, actually. So I'll jump straight into those and read them out to you. So the first question comes from Peter Wolfgram. Where would stainless steel electrodes fit in your electrode noise summary graph?
Yeah, I won't bring that back up again. Relatively highly amongst the metal electrodes. The study that I did show, I think that was more from the area of sort of complex resistivity IP electrodes. But in that study, the sort of comparable acid-free electrodes, which is sort of comparable to the stainless steel, showed fewer spontaneous jumps compared with, say, a steel electrode. So stainless steel would fit in relatively highly amongst the metal electrodes.
Okay, yeah. And then we have Didas Makoye. Good presentation. In case there is the problem of the phase shift caused by the contact resistance, as you explained, can such data be reliably used? Recent MT surveys on the Tanzanian craton, we have encountered a similar problem where the phase is offset in the mid frequencies or even longer frequencies. Therefore, it seems this problem is not only constrained in high frequencies.
Yeah, I guess there's multiple parts of that question. The effects of the contact resistance capacitance of the wires, that would be expected to be a high frequency effect, just sort of an RC type circuit. So I expect that the sort of mid-range frequency response is probably a different effect and possibly associated with signal to noise ratio and levels. Can those be corrected? In the first case, I think you could possibly make some theoretical corrections, but only for a small part of that frequency range. The fall off in the MT response rate, the example from Baffin Island, for instance, was over several decades in apparent resistivity. So at the highest frequencies, the actual signal levels were a factor of 10 or 100 smaller than they should be. And I expect at that level, it's just simply not possible to make the correction. However, if the effects of the electrodes and so on are more like, say, a factor of 3 or 4 or 5, it may be possible to make some correction. I know in a lot of electrode studies, the electrode responses, and this is sort of from medical fields and other fields, the electrode responses are measured as a function of frequency and then represented by equivalent circuits. And so defining those other components of the equivalent circuits, the capacitance, the resistance, and so on, would enable some correction of the correct resistance. So I think the answer would be a little in the case of true sort of RC noise. In the case of something happening at mid-frequency range, as I said, I expect that might more be a signal to noise aspect. And that may be, there would be, apart from remote reference type methods and applications, much less scope for making a correction there.
Yeah, and I suppose, it goes back to one of your comments, also looking at the time series to see if you can maybe see some broadband noise source there, because of course, as you said, there are many effects that can cause something like that, and these RC effects are just one possibility. Yes, that's essential.
Yeah, and probably when for the study we had in northern Manitoba, looking at the impedances calculated using a remote reference electric field, remote reference magnetic field, looking at the local electric field processing or local magnetic field processing, looking at those 4 different responses provided some information on the source of some of the problems that we're seeing in the data. So
yeah, and actually, I'm going to skip Dennis's question because Jan Avram was writing something which, of course, also plays into this. So he's saying the observation on the midband phase issue could be related to a large conductive body at depth causing the phase rolling out of quadrant. Of course, there's all that sort of on top of everything else.
yeah, I didn't even get into that.
Yeah. So I think the summary is, yeah, yes, possibly, but make sure you know what you're actually sort of looking at there before you try to correct anything. Yes, because it could even be earth structure, right?
Yes.
Okay, and then we have Dennis Woods. What is your opinion of using squids for AMT, BMT, LMT, beside the logistics of liquid helium or liquid nitrogen? Bandwidth, low noise advantage, stability noise, calibration, etc. PS, great to see a photo of a Goff Reitzel after what, 40 to 45 years?
Yeah, I think Dennis is probably in a better position to answer that question more than I. About the squids. Certainly the technical capabilities I think are very good. And in fact, I should have mentioned that in Alan's presentation, he showed a summary of sensor noise from Discovery International, and the squids, really good specs in terms of measuring responses at very low signal levels. So I think that there is some potential, particularly for studies in which signal level is very low, and the technical specs of squids would certainly be adequate for making those measurements. Again, there's going to be some slight differences in terms of recording a total field rather than a time derivative that need to be sort of dealt with. I don't know about the how rapidly measurements can be made with a squid, and whether it be possible to look at using squids to try and fill up the AMT sort of deadband or not. And that's something Dennis could probably answer better than I. But that's probably where one of the greatest challenges would be in terms of recording good data, would be in that period range. And of course, there's also CSAMT and sort of other things that you could use at that point also. So I think technically, yes, the practical issues of portability and logistics would be a factor that need to be considered there.
Yes, and I think those are reasonably big ones, right? Depending on where you're going. Yes. Okay, there's a reply by Didas. I recommend if you want to discuss this further to also sort of exchange emails. So he's just saying that, yeah, he also sees that apparent resistivity curves become very conductive. I suppose he means sort of, yeah, very low apparent resistivity. I think again, word of caution, make sure you know why that is, maybe from a spectrum and time series point of view. At the moment, there are no questions, but I'm going to ask you something. I mean, Adam Schulz sort of told us a bit where he thinks things should be going. So what is your opinion on that? Sort of, where are things moving? Where should things be moving in terms of data acquisition? Where are the biggest gains to be made? Do you have any opinions on that?
Yeah, I was sort of thinking a little bit about this sort of thing before the talk, and as I said, I think the three biggest gains that we've had in the last few decades have been basically the data storage volumes. The A to D has been important, and the GPS has been really important. In terms of processing, of course, the remote reference approaches and the tensor decomposition approaches have significantly improved MT data. To some extent, yeah, coils and electrodes have improved a bit, but not perhaps as much as those other factors. I guess if I compare things with seismic reflection, over the last, say, 30 years, the volume of data we collect has probably increased from tens of kilobytes up to hundreds of megabytes. So I guess ask the question, have the responses sort of improved by that root n factor, assuming that there were random problems in those responses that we would see. So we probably should have seen, a factor of 30 or 100 times improvement in our MT responses, given the volumes of data that we're now collecting. And the question is, have we? We've certainly seen a lot. That's often come from remote referencing and those aspects. We've got slightly broader period ranges in our responses. But I think the actual sort of background broadband MT range is that we haven't necessarily improved as much as root n would suggest that we should. So I think there's probably still more room for smarter processing rather than smarter acquisition. And that's something that perhaps there should be at least a dual focus looking at that at the same time as looking at the actual instrumentation in the field. Certainly, I agree with many of the aspects that Adam said, that we need to be faster and sort of have more sites. Again, the total number of sites comes back to sort of the relative level of geological noise versus our targets too. That we may reach a point where there isn't that much value in having too many more sites. But certainly for 3D coverage of areas, yeah, we certainly need more the ability to record more sites in targeted areas. But as mentioned, I think we should also think about some of the smart people out there about processing and optimizing processing and those sort of aspects also.
Yeah, and I mean, certainly that's a very interesting sort of comment of yours with a square root of n, because yeah, from my experience, I would also say data from the 90s, let's say, it's not unusable. Yes, it's from a modern perspective. You wouldn't say, oh, don't even look at that because we've become like 10 times, 100 times better. But very often you're like, okay, yeah, they're not the greatest, but they're fine. So that it suggests that there are other limits possibly, and yeah, dealing with outside noise is probably a big one. There's another question from Jan Avram. Hi, Ian. Any comments on sampling rates, continuous sampling versus decimated sampling rates? We tend to think the more data, the better. But is this true? I think it goes a bit back to your comment.
It's a good question, and I don't fully know the answer, and it'd be useful to have a broader discussion, I think, of this. If the extra data we're recording is useful data with good signal to noise and good characteristics, in principle, yeah, that should help the responses, and in that case, the more data, the better. However, recording or introducing large volumes of poor data, say data from times when signal levels were lower, into that same processing scheme may risk the data quality. So again, robust processing has obviously been a major advance in what we do, and maybe there needs to be sort of more development of robust methods to enable that higher volume of data to be used most effectively. So a very wishy-washy answer. In principle, yes, but again, we should be smart about it, I think is what I would say.
Yeah, and I mean, this actually sort of relates to something that I very recently experienced. So I was in Chile at the end of January, and geomagnetic activity, there was absolutely nothing. It was like, P index of 1 or, absolutely nothing. And then we packed up, and days later, there was a sort of a nice storm. Yes, and of course, that's, I think, in many cases, the value of recording for longer. Yes, you have, because it's random processes, you have a higher chance of catching something that gives you at least a segment of high activity data. So it's not necessarily the sort of extra n windows that you acquire of the same stuff, but that you acquire, a few hundred windows that actually have good signal. Yes.
Yeah. so multiple random processes being balanced.
Yes. Okay, I think that seems to be it for the moment. And of course, this will all be available. I think, yeah, we talked about you will send your PDF to Alan, so that can be looked at later. So thanks again, Ian. That was very interesting. And next week, remember, there's Raphael Rochlitz talking about modeling and inversion with, if I remember the name correctly, CusTM. So that's going to be a different aspect of MT. And yeah, until then, have a good day, everyone, and hope to see you next week.
Thanks, Max.